All right, ladies and gentlemen, here's the start of your chapter 33 notes. Probably go about halfway through the chapter, give you a break, and then move on with a second video a little bit later. But chapter 33 has to deal with electric fields and what we call electric potential. And essentially, electric potential, what we're going to find out is the voltage that we're dealing with. And electric fields are kind of like a gravitational field. It is just a uh, point in space where an electrical charge is applying some kind of force field around it. And so, anytime you have an electric field, it is a storehouse of energy. So, the space around any concentration of electric charge is different from, what you would be around if it wasn't there. If you've ever walked near something with a big electric charge on it, you may have noticed that, wow, my hair is starting to stand on end. Sometimes you can just do that with brushing your hair with a comb, or a balloon can be very have a high concentration of charge on it after you rub it on your head or something. This little device here on the right hand side of the screen is, I don't know what they call it. I have one, they call it an electric disco ball or something like that. And basically, what it is a Tesla coil in here, which can emit very large charges in the form of like electric lightning bolts from this thing that's pretty much like a Tesla coil. And it changes the gases that are inside of the ball into a plasma. And that plasma is created by the electric charge, generates a lot of energy into the gas and changes the colors of the gas. I would assume that the red is probably neon, and I think the blue is argon, but I'm not 100% sure about that. So, electric fields, what we look at here is the magnitude or strength of an electric field is measured by its effects on charges that are located inside of the field. And the direction of an electric field at any point by convention is what would its effect be on a positive test charge. So if I have something that's positively charged already, I put a positive test charge on it, the push of the field is going to be away. If I have a negative thing, if I put a positive test charge in its realm, it is going to be an attractive field. And so we have to worry about, it's a little bit different than when we talk about gravitational fields, because gravitational fields only work one way. They're always attractive, whereas electric fields could be either attractive or repulsive depending on what the charge is. So if you take a ball, you throw it up, it comes back down. Why? Because gravity acts on it. Gravity is creating a force field on that ball. And so because the ball is in contact with that force field, it is drawn back to the earth. You can sense a force field that is around a charged Van de Graaff generator. If I can get my daughter here for one of these, when I do like some demos next week, we'll try and get a Van de Graaff generator and blow her hair up like this little person is right here. It doesn't make it explode, but it may make it stand on end. And there's a picture in 33.7 of a lady who's got a pretty good charge. Mine isn't great, but it does a pretty decent job, especially if the weather's kind of dry. So an electric field is a force field, again, that surrounds an electric charge or group of charges. It doesn't have to be just one electron or proton, could be a whole clump of them. But when we think about gravity, again, a satellite is held to a planet by its gravitational force. An electron would be held to a proton by its electric force field. And so the proton being a positive charge, the electron being a negative charge, the attraction is there. Now, if we took two protons and tried to put them together, they would push each other apart. So the field would be one that pushes them apart rather than pulls them together. Now, an electric field has both magnitude and direction. The magnitude, again, is how strong is the push. The direction is which way is it pushing, obviously. But we always do or determine which way the direction is headed by how would my object that I'm wondering what its field is, how is it going to react when I put a positive test charge near it? Again, if it's a negative charge, it's going to push it or pull it towards it. It's going to be attractive. And it is going, if it's a positive charge, it is going to push that away. And the force is always greatest, has the strongest magnitude the closer you get. And then the test charge, it's the weakest, the farther and farther away that you get. So the direction of an electric field at any point by convention is the direction of the electrical force on a small positive test charge. Again, we're always checking it with a positive test charge. So if the charge that sets up on the field is positive, the field is going to point away from the charge. If the charge that sets up the field is negative, the field is going to point toward the charge. So a question you'd want to answer here then is, how are the magnitude and direction of an electric field determined? Again, it's determined by how close are we and what is its effect on the positive. Is it going to be attractive or is it going to be repulsive? Again, attractive is if it's a negative charge, and repulsive is if it's a positive charge acting on that positive test charge. So 33.2 electric field lines. We did field lines when we talked about gravity. Again, how we draw these is either based on how far apart they are or how long we draw the lines. So these electric field lines are just a representation where we're trying to show what the field would look like. And again, the best way to do it is with your little arrows, those vector arrows that represent both direction and magnitude. Again, direction, which way is the arrow pointing? Magnitude, how long is the line or how far apart is it from other lines, would tell you if it's strong or weak. Now, since in an electric field we have both magnitude and direction to think about, it's a vector quantity, and we can represent it with vector quantities. Negatively charged particles surround vectors that point toward the particle. Positively charged particle vectors would point away, again, because we're testing that positive test charge. Magnitude of the field, again, shows a vector with longer length for bigger ones and smaller length for or shorter length for smaller vectors, for smaller fields. So you can use these electric field lines to represent the electric field. Basically, for different situations, we'd want to kind of show different things. Where the lines are farther apart, again, it's weaker. If we have an isolated charge, the lines extend to infinity, just like, the planet Zoltan is affecting you with its gravity. It's very, very minimal because Zoltan is so far away. But basically, again, these extend to infinity. There might not be much attraction or repulsion on you from the electric charge, but it's always there. So if we have two or more opposite charges, the lines are going to come from the positive charge and end on the negative charge. So we've got some diagrams here to show some of these things. But basically, A represents, again, a negative object. So it's going to be attractive field lines, again, longer lines toward the closer we are, shorter arrows, vectors, the farther we are. And then again, if we look at this one here, it's basically the same thing, because here we just see that they're farther apart than they are here. When they're farther apart, there's less of a field. When they're closer together, there's more of a field, stronger field. So when we have a positive charge, again, that positive charge would be pushing away a positive test charge. So our lines would be, for our vectors, would be going away. And then when we have a positive and a negative charge, always have the field lines moving from the positive to the negative, positive to the negative, as the arrows show there. And then there's also the possibility that we have something like this. Anytime we have, these would be capacitor plates, and in a capacitor plate, it's always moving again from the positive to negative. But we see at the ends that we kind of have that charge beginning to bulge out. It's beginning to try and leave the system, but it always wants to move from the positive to the negative. And so we can set up some different scenarios where we set up electric fields. And what we have again is a situation where there is a equal but opposite charge. Again, one positive, one negative. These little gray bits, blacker on the gray, on the white, whatever it looks like to you, basically are lining up in that field that we saw back on a page or so back there. Here, what we kind of see is two equal but opposite, or equal but the same charges. And so there's kind of this wall in between them where these little gray bits are trying to avoid each other because of the repulsion. Here we have some capacitor plates. We can see it bulging out on the end and then moving from positive to negative through the situation. And this one kind of is something we're going to look at a little bit later. When we have something that is circular, it sets up a shielding effect, and that shielding effect keeps any any field from developing. And so we can see a field outside, but there's nothing going on the inside here, and that is a result of no electric field being set up inside of the circle. And so those are just bits of thread that are set up in a little oil bath, and the different scenarios I just described to you. I'll leave this up for a second. You can pause it if you need a little extra time there. And then what would happen if I took an electron and I blasted it through two capacitor plates, one being, again, positively charged, one being negatively charged? Well, basically what we see is the beam hitting here. If the charges were reversed, I put the negative up here and the positive down here, what's going to happen? Well, it's going to cause it to drop down. Why does it drop down? Again, the positives are attracting the negative electrons, and the negatives are repelling or pushing those electrons away. So how do you represent an electric field? Again, with these field lines, does the trick. Again, arrows showing the direction, and length of the lines showing how strong it is, or how far apart they are, showing how strong it is. So electric shielding, when we have a charge, it's on a conductor and it's not moving, the electric field inside that conductor is zero. And so all of your electronic devices, your radios, your cell phones, all those kind of things, all have shielding on the inside of them. If they didn't, we periodically walk through these electric fields, and it would mess up all of the components in your radio, in your cell phone, if you walk through one of those. So what they do, what the manufacturer does, is he puts it's almost just like a aluminum foil on the inside of your phone to protect all those sensitive components, so that if you walk through an electric field, you don't get, everything going haywire and, shorting out on you and, not working anymore. But one of the safest places you can be in a thunderstorm is in your car, for a couple of reasons. One, the car provides shielding. The rubber in the tires is also an insulator, so it doesn't allow grounding to happen very easily. One dangerous condition, if your car is in disrepair and you've got any wires dangling on it, off of it, and things like that, you might want to fix that, because if you are ever in a thunderstorm, you're not going to be as safe as you think. It may actually bring the electricity down in through the car and make you kind of a lightning rod, and you don't want that. So try and keep your car in good working condition and doesn't have wires. Or I remember one time back in the old days, I used to lock my keys in my car a lot, so I would wrap a wire hanger around my tailpipe. And one time I discovered that it was dangling on the ground, and not only was it throwing sparks, but it was also, doing some other things that could have been dangerous, like electrocuting me in a thunderstorm if I ever was hit. So ground charged conductors, in the absence of an electric field, what we see is that inside of that conductor, we hold static charge, and it's not an inability of the electric field to penetrate the metals. And so free electrons within the conductor basically settle down, and they stop moving when we have these conditions where the electric field is zero. So the charge is arranged to ensure a zero field within the material. And so if you ever have a circular spherical cavity inside of the cavity, is going to be shielded. The reason being that any electrons that are around are going to distribute themselves equidistant from each other. And so any effect that they're throwing on the inside is canceled by the exact same thing that's happening on the outside. And it's perfectly obvious in a sphere, but what turns out is it doesn't have to be a sphere. It can be any shape. Your cell phone obviously isn't a sphere, yet the shielding that they wrap stuff around, the little aluminum foil that's wrapping a lot of the components in your cell phone, is definitely not in a spherical shape. And that's because it doesn't have to be. Anytime you are inside of a metallic, what do I call it? A metallic dome, a metallic room, you are shielded from outside effects of electricity. There's no field on the inside, so you're protected. So how do we shield an electric field? It's pretty simple. Basically, all you have to do is surround yourself or whatever you want to protect with some kind of conducting surface, usually a metal. There was a strange man that used to walk around Reading when I was a younger kid, and he always wore like an aluminum helmet, aluminum foil helmet, and he thought it was to protect himself from signals from the government and things like that. And he was, from what I understand, he was very bright and he understood this shielding thing, but I think the purposes he was doing it for was because he was a little on the crazy side. But anyway, free charges on the conducting surface are going to arrange themselves on the surface of the conductor so that the field on the inside cancels out. And so here we have a cable. This might be like the cable that is bringing signals from cable or your satellite system into your television, you can see that there's a foil wrap there. There's a foil wrap on, I don't know if this is a cell phone or a radio, whatever it happens to be, but that is to provide a shield for the components that are on the inside. Without this shielding, or if your shielding ever gets damaged on your cable, basically your signal can be disrupted by somebody turning on a blender or something like that inside the house somewhere, and it can make your picture all fuzzy when a blender is turned on. It's usually because this shielding has been damaged somewhere. So it's said that a gravitational field, unlike an electric field, cannot be shielded, but the gravitational field at the center of the Earth cancels to zero. Isn't this evidence that the gravitational field can be shielded? And the answer here is no, because gravity can be canceled inside a planet or between planets, but it can never be shielded. And that's because shielding requires a combination of both repulsion and attraction. But because gravity only attracts, it can go to zero, but it's not shielded. So how can you describe the electric field within a conductor holding a static charge? It should be zero because it will be shielded. Now, electric potential energy, or EPE, is the energy of a charged particle as it's increased when it's moved inside of an electric field. And so basically, the way to think about this is if I have a proton and I'm trying to move it closer to another proton, I am going to increase its potential energy the closer I bring it, because it wants to repel. And so as it's wanting to push away, the harder I'm pushing on it, the more work I'm doing to it, the more electric potential energy it is picking up. Then if I let that proton go, essentially what would happen is it would fly back away. It would pick up the electric potential energy that I gave it and turn it into kinetic energy and push it back away. So work is done when a force moves something in the direction of the force. An object has potential energy by virtue of its location, say somewhere inside of a force field. So for example, doing work by lifting an object increases its gravitational potential energy. And so we take the thing, we lift it up, gives it more potential energy. As soon as I cut the line, though, it comes zipping back down, changing into kinetic energy. Well, if I were to take a positive charge and a negative charge and begin to separate them or pull them together, if I were to cut the little wire that was holding the positive charge, the two would come flying together as a result of the kinetic energy that was gained by the potential energy that had been gained moving them apart. So a charged object can have potential energy by virtue of its location inside an electric field, and work is required then to push a charged particle against the electric field of the charged body. If I try and push a positive charge closer to a negative charge, that's actually it's actually going to pull my hand if I were to not give it much resistance. But if I try to pull that away, it doesn't want to pull away because they are attracted. And so to push a positive test charge closer to a positively charged sphere, we're going to expend energy to overcome that electric repulsion. And so work is done in pushing the charge against the field, and this work is causing a gain in the electric potential energy. And so any energy that a charge has due to its location is what we call electric potential energy, very much like gravitational potential energy is due to its position in the gravitational field. So if the charge is released, it's going to accelerate away from the sphere, and it's going to go flying back away as the potential energy we have given it is changed to kinetic energy in it flying away. So how can you increase the electrical potential energy of a charged particle? Again, either move a positive further away from a negative or move a positive closer to a positive. So that's a good place to stop for now. I will get you the 33.5 through 33.7 shortly.